This is a recording of section 3.1. There's only going to be one recording for this section, and it's about describing relationships. It's specifically, it's trying to delve in to try to describe the relationship between two variables, and both of those variables are going to be quantitative. So in chapter one, we looked at how do you compare two variables when they're both categorical. Now we're going to look at quantitative variables. Now we're going to start with this idea that when we're trying to describe the relationship between two variables, there may be an explanatory variable and a response variable. In this definition, the response variable measures the outcome of a study, where the explanatory variable may help explain or influence the influence changes in the response variable. Think about it this way. Does the number of minutes you exercise help explain your weight? Okay. Are the number of minutes that you study for the next test help explain your test score? So in some instances, there's a clear explanatory response relationship. And most of experiments involve trying to track down and figure out those relationships. Um, Let's take this idea. Julie asks, can I predict the state's mean SAT math score if I know the SAT critical reading score? Jim wants to know whether the mean SAT math and critical reading scores are related to each other. For each student, identify the explanatory response variable if possible. Well, in the first situation, when we talk about Julie, Julie wants to do prediction, okay? And she wants to use the SAT critical reading score to help predict the math score. So in Julie's situation, we might say that SAT critical reading score predicts the SAT math score. And when we ever have this model, we call the SAT critical reading score, we call it the explanatory variable. And the SAT math, we would call the response. Whenever we do prediction, the variable we use to make the prediction is an explanatory, and the one that's getting predicted is a response. But Jim's question, simply saying, is there a relationship? He's not trying to say a predictive relationship, and do we think one comes before the other? And for Jim, we might say there is no clear explanatory response relationship. One doesn't clearly follow the other relationship. It's not like exercise precedes weight gain or loss. It's not like studying precedes doing well on a test. So not every quantitative variable has an explanatory response relationship. Let's go on to the next page. So in the next page, how do we get to find out if there is a relationship, regardless of whether it's an explanatory response relationship or not? And the best way to look at that relationship graphically is a scatter plot. Now, a scatter plot shows the relationship between two quantitative variables measured on for the same individuals. The values of one variable appear on the horizontal axis, and the values of the other appear on the vertical axis. Each individual is a dot, a point on the graph. If we do have an explanatory explanatory response relationship, we will put the explanatory variable on the x-axis. Let's see this in practice. Ninth grade students at Webb School go on a backpacking trip each fall, and students are divided into hiking groups of size 8 by selecting names from a hat before leaving. Students and their backpacks are weighed. Here are the data from one recent year. So we have a student, one individual that weighs 120 pounds, and their backpack weight is 26 pounds, and so on. And since in this relationship, do we think that there's an explanatory response relationship? Well, yeah, I think that body weight is an explanatory variable because someone who is bigger, they are more likely to be able to lift more. So body weight is my explanatory variable. So therefore, I'm going to put that on my x-axis. Now, in terms of figuring out how I'm going to lay out my scatter plot, I might start by saying, well, what is the minimum and the maximum values that I'm seeing for my x-axis variable, for my explanatory variable? Looks like my smallest value is 103, and my highest value is 187. Okay, so I need to think about how I'm going to lay out my scale on the explanatory on the horizontal axis, so I get all the numbers between 103 and 187. So I'm going to try starting at 100, and let's say I go up uh, every every two ticks is going to be 5. So this would be 110. So it's 115. Here's 120. Hopefully I'll be able to get everything in. Here's 130. Here's 140. Here's 150. Am I going to make it? Here's 160. Oh, I'm going to be a little bit short. All right, let's tighten this up. Let me get rid of these numbers and let's go to this is 110. This is 120. This is 130. This is 140, 150, 160, 170, 180, and 190. And that's big enough to get my largest value, 187 on there. So I've used a good portion of the horizontal axis. Let's go ahead and do the same thing for the backpack weights. My smallest backpack weight appears to be 24, and my largest one appears to be 35. So I gotta get the numbers between 24 and 35 on my axis. Let's put 24 here, 25, 26, 28, 30, 32, 34, and 36. And so I have now room on both things. Let's go ahead and put, so this is my body weight measured in pounds. And over here is my backpack weight. And that's also measured in pounds. And now for each of my individuals, I'm going to plot the data. So 120, here's 120, and up 26, and there's one of my data points. Let's go on to the next one. 187. So it's 185. 187 is about here. And then 30 is about there. So there we go. Second point. 109.26. 109.26, about right there. 103.24. 103 is about here. 24 is right there. Again, every individual gets a point. 131 and 29. Put me right about there. 165, which is here, and up 35, which is seems to be right about there. Yep. 158 and 31. Put me right about there. And then last one, 116 and 28. Right about there. All right. And there we go. Um our scatter plot. And then what do we do with plots? Well, we try to make sense of data. When we have plots for distributions, we do things like socks. Well, as we look at this particular data, we're going to be having a new set of ideas to make sure that we uh, interpret them correct or in a way that the College Board likes. So, what are we looking for when we're looking at a scatter plot and we're trying to make sense of it? We're looking for an overall pattern, and that pattern comes in the form of a direction, a form, and a strength. And we'll go through what each of those words mean. And then we'll also look for departures of the pattern. So we'll be looking for outliers. Okay. So in the scatter plot that we just did, I would describe the relationship of body weight to backpack weight, straight to be, I call it strong. And what does that mean? It means that the relationship seems to be pretty consistent. A direction, I would call it positive. Why would I call it positive? Because in general, as we go from left to right, the trend of that data is going upward. The form, I would say, is linear. Now you're saying that doesn't look like a line. Well, again, if we look at the general form, most of these points are pretty close to being in a line. This guy doesn't fit that pattern. I would say that the backpacker who had the 187 um, pound with the 30-pound backpack is an outlier. It does not fit the general trend. All right. Now let's dive in a little bit deeper as we talk about, well, what do we mean by those words that I just used? We say that two variables have a positive association when above average values of one tends to accompany above average values of the other, and when below average values tend to occur together also. So if we go back to this thing, if we think about um, where is above average for backpack weight? Where is above average for body weight? And look at those guys, they tend to kind of clump together in the low body weight, low backpack weight. And these are kind of clumped together in the high body weight, high backpack weight. And so that's what we mean by a positive relationship. A negative association is when above average values of one tend to accompany below average values of the other. Let's see if we can do and look at this new data set and do the same kind of description. The scatterplot was constructed using the mean SAT score for each state against the percent of the state's high school graduates who took the SAT. Not every, not every state forces their students to take the SAT like Michigan. And so some states, very few, 10% or less of the state takes the SAT. And they seem to be associated, these low percentages, with pretty high mean math scores. And with a higher score, a higher percentage, there seems to be lower scores. Well, I would describe that direction then, I would describe that direction as being a negative direction because above average of one variable is associated with the below average of the other. Now, what about the relationship here? I'm going to switch over to a much sort of thicker marker. And I could think you could see a general pattern, and that general pattern looks to be curved. All right. So there is a form, but it's not linear in this case, it's curved. And how well do the data stick to that general pattern? I would say that it's also a pretty strong relationship. Okay. Are there any outliers? Are there any values that tend not to follow the general trend? Well, this one right there seems to be a little bit away from that general curve pattern, as does this one. So I would say the one that looks to be about 18% taking with an average score of 500, um, or the one where it looks like about 90 or 80. I'm going to say 87% are taking, and it seems to have a average score of about 460. Those look to be outliers in that they're outside the general trend. Let's go on and take a look at the next example. It says manatee are large, gentle, slow-moving creatures found along the coast of Florida. Many manatees are injured or killed by boats. Table below contains data about the number of boats registered in Florida in thousands and the number of manatees killed by boats every year from 1977 to 2007. If we want to um, find the relationship between boat registrations and manatee deaths slash injuries, then our plan perhaps would be to start by making making and interpreting a scatter plot. Interpreting, interp, int, the scatter plot. Now, luckily for us, the book has made a scatter plot for us, so we don't have to plot that out. So there's our do. We made this, the scatter plot is made, and then what would we conclude? What's our conclusion? What's our feeling from looking at this? There is a, I would call it a strong, meaning it looks like it tightly adheres to a particular form. Certainly positive is one variable goes up, the other variable goes up. And it sure does look like a linear relationship. And then let's make sure we add context to our answer between, and for some reason, we typically give the response variable first, manatee injuries, and the X variable second, and that is, and boat registration. All right. Now, how do we talk about the strength of the relationships? Well, if we limit ourselves to only talking about relationships that are linear, then we use a particular word called correlation. Now, watch out because correlation gets used loosely by a bunch of different other in other situations. But in statistics class, when we say correlation, we're always talking about the strength of a linear relationship. Let's take a look at what the book has to say about correlation. Correlation, and we're going to use the letter R to represent correlation, measures the strength of a linear relationship between two quantitative variables. R is always a number between -1 and +1. If R is greater than 1, that indicates there's a positive association between the two variables. If R is negative, there's a negative association. Values of R near 0 indicate a very weak relationship. The strength of the linear relationship increases as R moves away from 0 and toward either -1 or +1. Extreme values of -1 and +1 only occur when there's a perfect linear relationship. And so, unfortunately, you're not going to be really good at judging correlation in the short term, but here are 6 different examples. And you can see from a situation where there's a weak relationship or no relationship, correlation 0, to these kinds of weak relationships. So you can see a slight general negative trend there. And as they tighten up, the numbers get bigger. Even though this doesn't look very tight, it's got a pretty good R value, meaning it's relatively close to -1. And here's something that's nearly perfect in its correlation, -0.99. Okay. What I would like you to do is I'd like you to associate particular R values with particular adjectives. So I'm going to draw out a number line, putting -1 and +1 on the two ends. And we're going to say that if you have a -1, you have a perfect negative relationship. Whereas if you're down here, +1, you have a perfect positive relationship. Now, smack dab in the middle is 0, where we say that there is no relationship. We're going to split these two sides into thirds, and I'm going to put 0.7 and 0.3, and these are just my numbers that I use roughly. We're going to say anything that's got an R value bigger than 0.7, we're going to call that a strong relationship. If it's positive 0.7, we'll call that a strong positive relationship. Down at this other end, we're going to call these a strong negative relationship. In between 0.3 and 0.7, I'm going to call this a moderately strong relationship. So for positive 0.5, I call it a moderately strong positive relationship. For being between -0.7 and -0.3, I'll call this a moderately strong negative relationship. And then in between -0.3 and 0, I'll call that a weak relationship. Weak negative on this side and a weak positive relationship on this side. So that gives us some adjectives to attach to this measurement of strength of linear relationship, which we call correlation. Now you may ask, well, how is this correlation calculated? Well, here's the formula. Um, it looks really complex, but let's just sort of kind of dive in to see what we can see. First of all, there's our R. That's the letter that we use for correlation. We got a division by n-1, and n is the number of individuals that we have in our data set. Okay, let's take a look at this part right there. Okay, it takes an X data value, subtracts it by the mean, and then divides that by the standard deviation. Well, we have a name for that. That is the z-score for data item X of 1. And if I circle this one, a y data value minus y bar minus s of y, you might recognize that as the z-score for y sub 1. So what we have is that we have these two z-scores and we're multiplying them together, which has an interesting idea because if this is x bar and this is y bar, if I grab a number, let's say out of this area, it's got an above average x bar value, it has above average y bar value. Oh, sorry, the data values are above x bar and y bar. So we get two positive z values because z values are positive if you're above average, and that ends up giving us a positive value. If we're down here, we have a below average x multiplied by a below average y. We got a negative times a negative, we end up getting a positive value. So essentially, if we have above average and below average, sorry, double above or double below, we end up getting a product that only returns positive values, which is one of the reasons why that R is positive when there's a positive association. Now, if we switch over to red and we do the same thing, this has a below average X with a positive y. This is an above average x with a negative uh, z value coming out of the y's. These give us negative values, which means if your below average value of one variable associated with a high above average value of the other, you're going to end up getting negative numbers out of those products, and therefore it's the reason why the R value tends to be negative. Now, if we go and take the backpacking example, we can actually go through and by hand calculate the correlation value. First thing we need to do is go through this data and find the mean and find the standard deviation for the body weight and for the backpack. Here's there it is. There's the mean value for the body weight. Here's the standard deviation of the body weight. And here's me taking the body weight when 120, we'll subtract it by the 136, divided by the 30.2, and we get negative 0.53. And I could do that for every one of the body weights. Oh, one of them's left blank. Let's fill that in. 116 minus the 136.125, the average body weight, and subtract it again by the standard deviation of the body weights, 30.96. And if I break up my calculator, this ends up being negative 0.66. We could do each of the same things with the backpack weights, using the average backpack weight being about 28 and 5/8. The standard deviation for those backpack weights being about 3.5. And again, for each backpack weight, take it, subtract it by the mean, divide it by the standard deviation, get a value. The last one is left open again. That's 28 minus 28.625 divided by 3.462. And if we do that calculation, we end up with negative 0.18. Oh, take a look at that. Let me just highlight that in green. The 116-pound person is below average in weight, and their 28-pound pack is below average in backpack weight. That's a double negative. Multiply those together, we end up getting that positive, which ends up influencing the the R value. If we put those in there, say, okay, this is negative, let me zoom in a lot, negative 0.66 times negative 0.18, and add that to our big long calculation with all of those products and dividing it by 8 minus 1, we find out that the R value is 0.794. Okay, we now have an R value. Can we interpret that in context? Well, we saw the relationship was linear, so we might say that backpack weight and body weight have a strong positive relationship or association. Okay. What effects would removing the hiker with the heaviest body have on the correlation? Justify your answer. Well, if we remove that outlier, the one that doesn't fit the trend, um, the correlation, meaning the strength of that linear relationship, correlation would get stronger. I'm using the word strong here as compared to getting bigger, because remember, a strong relationship could get, if you're already positive, it gets more positive. But if the relationship was negative, it would actually get more negative. So we'd like to use the word stronger as compared to bigger. I actually did calculate this. The old R value is 0.79. The new R value is 0.946. So indeed, it got stronger. It got, in this case, more positive. All right, some facts about correlation. Correlation makes no distinction between explanatory and response variables. So no matter whether you flip them around, it gets you the same R value. Correlation does not describe the curve relationship between variables, no matter how strong the relationship is. Again, R values correlation strictly for the strength of linear relationships. Correlation is not resistant, meaning outliers strongly affect the R value. And lastly, correlation is not a complete summary of the data. What do you need to do to get a complete summary? You need to plot the data and interpret that. All right. Again, you don't have a lot of experience assessing R values. We're going to do these four, and we're going to say, hey, can you guess the R value? Take a look at that one. Okay. First off, looks positive. So I think the R value is going to be positive, but how strong is that relationship? What's your guess? The correct answer is 0.9. Pretty strong relationship. Let's take a look at the second one. Okay. There does seem to be a sort of a general upward trend with the data, but it's certainly not as strong. What do you think the R value here is? The answer is 0.5. How about this C one? Seems to be a little bit of an upward relationship, but certainly not as strong as either of the other two. When you calculate the R value of this, it ends up being 0.3. This one. I see a slight downward trend, and certainly those points are pretty far away from the data. As you may expected, this R value is not only negative, but it's pretty weak. Ends up being 0.1. Hope you guessed well. All right. In summary, when we're trying to explore the relationship between two quantitative variables, we use a scatter plot as our device to try to summarize that data. If there's an explanatory response relationship, we try to look for it. And if so, we put the explanatory variable on the x-axis. When we try to summarize or interpret a scatter plot, we try to do so by talking about its direction, its form, and its strength. Direction is either positive or negative. Form is linear or curved. Strength ranges from strong to moderately strong to weak. We have a quantitative measurement called correlation, which helps describe the strength of linear relationships. And we have all of these attributes for the R value. And that concludes our lecture for section 3.1.